Thanks, Kate. I'll say that a member of the class of 2002, so we're going to get all the twos. I apologize to the sevens, but I got a lot of twos references today. A member of the class of 2002 actually, as a kind of a graduation gift to me, presented me with a giant photon modeled after the same one. So there you go. What I will tell you today is mostly about art and mostly about Hodge, but I might sneak in a little chemistry too. Stay with me. So what I'm going to tell you about in particular, 715 Molecules, is a table. It's a table by the artist Jenny Holzer, who has an honorary degree from Williams, not in a 2 or a 7 year, but she has an honorary degree. And of course, Hodge Markgraf is the class of 52. Do we have any 52 people in the audience? You might have seen the talk before, but I put in some new things. Thanks to the class of 52. I'll also do a little public service announcement. On Saturday, I'll be part of the art tour, where you can walk around campus and see some of the public art. The class of 61 gave, as part of their reunion gift, gave a public art fund, which includes this piece right here, viewed from the side, George Ricky's double L eccentric gyrorotatory. Now, you might not recognize this because there's a really nice tent for the class of 62 right there. The table I'll be talking about is over here, is the middle stop on the art tour, and the first stop and the starting point for the tour is the eyeballs, formerly called eyes. Louise Bourgeois' piece right at the entrance to WICMA. So you can see Lawrence Hall here. The start of the tour is somewhere over about there. So 2:15 tomorrow, Saturday, excuse me. A lesson I learned from Hodge was to be very thankful, very grateful. He was the master of writing thank you notes. I haven't mastered this myself, so I want to thank a whole bunch of people, and I'll note here that all the artwork and all the images are copyright by Jenny Holzer, and I'm very sensitive to the fact that there's a camera pointed at me, so I'll just vaporize, no. So images are copyright Jenny Holzer, the artist. Thanks especially to the class of 52. The class of 62, any 62 people here? Nice venue. Thank you very much. And thanks to trustee Kate Queenie for coming here. But there's a whole bunch of people that were involved in the project, some of whom are pictured here from the Holzer studio, who are people that I worked with. So the reason I'm telling you this story is because I was heavily involved in the project as a chemist, not as an artist. The project starts with Hodge Markgraf, and I suspect that Hodge Markgraf is known to most of you here, but you might have brought along a friend who isn't familiar with Williams, so I'll bore you with a few details, saying that he's a member of the class of 52. He was a professor at Williams for a very long time, and this is really kind of, this is officially when he retired. We had a big party. It was a reunion at that time in 1998, but he taught just about every year up until he died in 2007, either at Williams or at Duke or at MCLA down the street, Massachusetts College of Liberal Arts, formerly North Adams State, formerly Massachusetts Teachers College, part of the UMass system. The class of 62 may be aware he was the secretary of the committee which eventually recommended the abolishing of fraternities. He was the chemistry department chair for many years. He was the provost of the college. Many of you know him in his role as the vice president for alumni relations and development, which, like many things on campus, has been renamed. So I don't know what John Malcolm's title is, but same sort of thing. And he was marshal of the college. Hodge is really a chemist, and if you look in the background here, these are chemical structures. I'm going to show you a few of them, and there are 715 of them out on the table in the science quad. I'll make a note here. The connection with Jenny Holzer, when Hodge died, I was involved in helping to clean out his office, and it was filled with chemistry books and chemistry books and chemistry books. And the only books that weren't chemistry were two books by Jenny Holzer. But Hodge had a special connection with Jenny Holzer, and that's kind of how the table came about. Here's where, in a sense, the major connection started. Is Hodge was traveling in Berlin, and he saw this piece, the installation for the Reichstag, Jenny Holzer, 1999. And if you'll pardon my technology here, we're going to try really hard to make this work. We're not going to make it work that way. Sneak preview. Ooh, the Reichstag, there it is. Let's make it big and let's make it play. Play. Thank you. Ooh. So this is a particularly large piece, amber LEDs streaming text. And it's text from, selected by the artist and her team. It's text from the German parliament. And I'm told, I thought that the text streamed on the order of 8 hours, that kind of it would repeat daily. But I learned, Jenny Holzer was on campus this spring giving the Fulkerson lecture for leadership in the arts. And I'm told that the text actually streams for over 8 days before repeating. So let's see if we can return to the PowerPoint slides here. So the Reichstag piece then was a piece that Hodge first noticed, and it's been said of Jenny Holzer that you kind of remember the first time you see one of her pieces, that they can be very monumental, but they can also have an impact on you in other ways. I'm not going to show you some of the really scary Jenny Holzer pieces, but I'll just assert that there are some pieces of work that she does that are very disturbing. She uses themes of sex and death and war and kind of really big picture themes, but also kind of disturbing. But she's also very sensitive to the site and the venue, and she has spent a fair amount of time on the Williams College campus. Her spouse is an alum. She's been here. I'm going to skip over that one and say she's been given quite a few commissions at very interesting locations. You might recognize the Guggenheim in New York. This is one of her first really kind of breakthrough pieces, brought her to the attention of the general public, if not the art world. This particular piece here has two components. One is the LEDs, and these are amber and red LEDs that would stream around some of the text. Sometimes Jenny uses her own text, sometimes she uses the text of others. But I'll also note, just kind of as a foreshadowing what's coming, down below here, these red stone benches that are also inscribed with Jenny's own text in this particular case. You may know that Jenny also has a beautiful piece in the Guggenheim Bilbao, one of the permanent pieces in there. It's red and blue LEDs streaming, again, columns that are quite tall and narrow. And these particular columns, you can walk right next to them and kind of slalom in between them to see the pieces. A little bit closer to home, some of you may have seen Jenny's piece at Mass MoCA. Anybody see Jenny's piece at Mass MoCA, just out of curiosity? Jenny's piece at Mass MoCA. So what you can't see in this image, and I don't have a video of it, is that this text, so this is the large gallery at Mass MoCA. If you haven't been there, I encourage you to go visit, maybe even this weekend. The large gallery, so this is multiple football fields and multiple stories tall, but xenon lamp projecting text that streams down. And now in this case, it's not her own text. It's text of some poets, one who is shown here. And down in the middle, what you can't see very well in this image are beanbag chairs. And this is a very enjoyable, it's one of my favorite pieces that I've seen in Mass MoCA, is beanbag chairs, so you can sit back and relax and view the text. But when you leave, your impression remains behind, because the beanbag chairs bring in a little bit of technology. The beanbag chairs were made of a thermally sensitive material, so when you stood up, your imprint stayed behind for a few minutes. Jenny Holzer is good about using technology. Even closer to home, in fact, on display at WICMA right now, you'll see another sort of work that Jenny Holzer is famous for. You may have noticed that everything so far has involved English language text. I didn't show you text in other languages, but uses a lot of language. And again, we get the widescreen version, a little technology challenge here. There's a new projector, so this isn't really the aspect ratio of the piece, but sometimes Jenny's work can be maybe providing advice. So Jenny came to the attention of Hodge and vice versa, but really prior to that, Hodge was very involved in the new science facility, new, now 12 years old. Hodge was involved in the building of the Bronfman Science Center as an assistant professor. He was on the building committee, and he was also then asked about when the Morley Science Labs and the renovation of the Science Quad was done. He was involved. And one of the things that he was very interested in is making sure there would be some art in the Science Quad. Art in particular that would be reflective of the buildings and what was happening on the inside of them. I'll just say that there were some art projects considered prior to Jenny, but by 1997, and you'll notice this is a little bit before the Reichstag, they had the idea that there would be a Holzer LED piece in the area that's now Eco Cafe, or if you're the child of a class of 49, as I am, the class of 49 science court area was going to have some red LED strips around there. And I've actually seen drawings of that that the Holzer studio put up. Didn't quite happen. Year 2000 is when Morley was really built and constructed. And by the time Hodge died, so Hodge died in 2007, there was this kind of sentiment that there should be something on campus connected with Hodge. And several of us suggested, well, maybe now is the time to put the Holzer piece in that he was hoping for. And so at the time of 2008, the idea was that within the library, there would be one of these Reichstag towers, amber LEDs going from the floor 3 stories tall, and that students and faculty and staff would be, and alumni, would be involved in choosing the text for this, and that it would be the text of scientists talking about their own work, reflecting on what they had done, the impact of their work on society, on themselves, and maybe eureka moments when things had happened. And again, you'd get a long stream so that if you were in there down in the library studying, you would not see the same text unless you were there for semesters long. But about the time, 2008, those of you who are in the financial world, you might realize there's a challenge there. In 2009, sustainability became a big concern on campus. And the amount of energy that this tower would have taken was, let's say, significant. And it would have, the amount of heat it would have generated would, let's say, offset the heating needs for the building. But there was a nice meeting, I'm told. Bill Lenhart, the provost at the time, had the fine task of approaching Jenny Holzer and basically saying, oh, we can't do that. But it was a great meeting because she said, oh, well, that's okay. You know, I do benches. And so here's a bench, a Jenny Holzer piece, and it's in typical Jenny Holzer fashion. It's got a little truism on the side of hers. It says, you can't read it there, but I'll read it for you. It says, decency is a relative thing. Then somehow it came about that, well, Holzer also does tables. And the original plan was there going to be 12 tables, 12 benches throughout the science quad, and then it became one big table in the center of the quad. And about that time, it was still going to be text on the table. But there was some questions about, well, you know, Hodge was a chemist. Are there going to be any molecules or molecular representations? And, well, then it became no English language text and all molecules. So tables, what kind of tables? Jenny Holzer's done some tables. Anybody from the class of 72? I don't have any Williams 72 references, sorry. But, oh, Jenny is class of 72 from Ohio University. And here's a table that was installed a site-specific location. Jenny's a generous person with her alma maters and her honorary degree institutions. She had an LED piece and then decided that this new building they were constructing needed a table as well, so she installed a table kind of at her own expense. But here, I like this one. This table reflects an installation she had at the Venice Biennale where she won the Golden Palm for the best country exhibit. She was the first woman to represent the United States. And she had, among other things, her truisms in beautiful stone tables in multiple languages. And I'll just read the English. Money creates taste is the truism on this one. Text throughout here, but I kind of like this table even more. This is predates the Ohio table. This is at University of California, San Diego. Green table. It's made out of a beautiful Italian green marble that we thought we were going to get at Williams, but the contrast isn't quite quite the same. So we got a different one. And here's, you perhaps can read that one. Jenny Holzer's truisms have been used in a variety of venues. T-shirts, huge display screens carried by trucks, the Spectrocolor billboard in Times Square, projected airplanes, projected in xenon at Mass MoCA up on walls. I just pulled out a few that I happen to enjoy. Symbols are more meaningful than the things themselves. And Jenny hasn't always worked just in text. She actually did a little bit of painting, and she's returned to painting. I learned this year she's working in finger painting, kind of returning to her roots. I don't know. But that she's done a little bit of technical stuff. She said, at the time I was in love with a physicist, perhaps is the influence here, but her words and her drawing, what this brings out is a kind of a new sort of symbolism, and a new sort of text. And so now I'm going to give you a little bit of chemistry, a little sort of text that we use. So here's a molecule, one of 36 molecules known by the state of California to cause cancer, benzene. And it's different ways of representing benzene. So all these images are ways of representing benzene. And I brought this little bagel representation of benzene as well to show that there's a three-dimensionality to it, and the green, the bread part of this bagel, or where the pi electrons are located. I brought another molecule of benzene to show you. Kate mentioned that really what I'm interested in dynamics is movement, that we've got static images, and really balls and springs are a pretty good metaphor for the way molecules look. And it's a pretty good text for chemists to show that they're constantly moving. They never stop, not even at absolute zero. Pretty remarkable. But the representations, all these are different ways of representing benzenes, molecule which has 6 carbon atoms and 6 hydrogen atoms, connected with either a double bond or a single bond, or really a hybrid of the two. Mercedes benzene here we sometimes use. No, this is a contemporary atomic force microscope. Actually, this is a scanning tunneling microscope image of actual benzene. Here's the balls and stick representation. Here's a simpler representation right here. So this one, giving it the red highlight, is the sort that actually was chosen by Jenny to use on the table. A lot of discussion with chemists, of course. Here's kind of what prompted me to ask the Holzer studio about molecules, is noting that Hodge Markgraf's tombstone, gravestone, which he designed, or grave marker, which he designed, Nancy and Hodge, has this molecule on it. The molecule is pyridine, which is a nasty, smelly molecule. You might wonder why he chose it. He chose it because it's the simplest nitrogen heterocycle. It's the simplest molecule that has a nitrogen atom, and that was really the subject of Hodge's life work. On the table, it appears, well, you can see there's a picture of pyridine on the table. That's the stone that was ultimately used. And so here's a different language. When Jenny Holzer was given the commission for a piece that was given by the friends of Hodge Markgraf, she took a look at Hodge Markgraf's notebooks, because looking for quotes, to put on an LED stream or to put on a stone bench. And Maggie Adler, who's involved in the project, kind of said, well, there's not a lot of writing in them. It's all pictures. And Jenny's comment was like, well, are they pretty? Can we use them? So here's an example of a notebook, a molecule. This is actually, it doesn't say it on here, but it's 1966, a molecule that I'm fond of because I wrote a paper with Hodge Markgraf about this molecule in the 80s. There it is on the table. And this is kind of what his notebooks look like. In fact, 50th reunion class, here's Hodge's notebook from 50 years ago tomorrow. Notebook entry, what did he do? Well, he was doing an acid cleavage of disultone, and there's drawing these little molecules. So here's a new language, a new representation, a new symbolism, and you can interpret the way you'd like. I think Hodge would like you to note it this way, and Kate mentioned this website, which is not available for me, but Greg Crowther has, and it's still up, actually, I checked it yesterday, quotations from Hodge teaching, some of which I like to adopt. Paper chemistry is cheap, and that's a reminder to me, I have a paper chemistry is cheap water bottle. purple water bottle, chemistry department swag this year. Paper chemistry is cheap, but stone chemistry is not quite so easy. It's like making real molecules. You can make a lot of drawings, but ultimately you got to go out in the field and you got to get some stone. So at Rock of Ages in Graniteville, Vermont, the largest source of memorial stone in the world, they were able to polish, and here's the table in progress, polish this beautiful stone, which is diorite. Why choose diorite? Diorite, well, here's some diorite. It lasts for thousands of years. So a famous example of diorite here is from the Louvre. Attribution of images. Ooh, date access, too. That's a good one. Don't always have that. But you can imagine how, this must have been really hard to cut, because I know how hard this stuff is, but it's lasted a long time. So the dedication plaque here, you can see sandblasted diorite, table and benches. Hope you'll take a chance to see it itself. But diorite brings me to a story. And so here I have to tell you a little bit of story and start to do some demonstration. So this is a, yeah, don't go away. Come back. Thank you. 1951, this is a paper for Chemistry 6 by Hodge, Markgraf, explaining polarization spectroscopy. So here we got a light source here, light going in every different direction. You put it through a polarizer, just like your sunglasses might have if you pay a little bit extra for sunglasses. You put it through a sample and they analyze which way the light has gone. I have giant sunglasses up here. You can see them. And if you shine polarized light through, cross polarizers, nothing gets through. But if you, oh, now I can see you. Maybe you can see me too. If you take a look there, you can play with these afterwards. So what we're going to do is we're going to do this same experiment, only now, in between these two sheets of paper, we're going to put a little bit of a sample. The sample, you may have seen this at science museums. You can put little plexiglass bridges there and put weights on them and watch them stressed, and you see some color. Here, the same sort of thing. We're going to do it with rock. We're going to do it with actually material that the table was made out of. So thanks here to Paul Karabinos, who did this experiment. And now we have to hope that we can find Paul's image right here. So you can go, there's the website. It's a real website. Why do we have to go on the internet to find this? Well, this is the website is Gigapan, and because it's actually an image that has many gigabytes of data associated with it. So this is an image, the actual chip of stone is very, very thin. I don't know exactly how thin, microns thin, and about an inch by an inch and a half in size. And if we do things, if we live right, we can take a look at this image, and you can say, why is it colored? The stone is kind of black-gray, and the answer is because we're viewing this thin slice between two sheets of polarized material, and so the different material is going to cause different light to come through. And then what we can do is, it's a microscope, we can take a look at it, and we can take a look at in detail of what the image looks like, and you can see different regions that correspond to different colors correspond to different types of stone. And then we've ultimately, of course, you run out of resolution. But if we work backwards, it's like shaky cam movies, you know, if you get dizzy here, just close your eyes. Okay, we're back. If you look at this image, and then if you talk with Bud Wobus, who's an expert on it, let's say, oops, there's a mistake. The stone isn't diorite. And if you do this full chemical analysis, which was done after the table was dedicated and the plaque was in place, and if you do that, it's not diorite. It turns out that it's a material which the geoscientists like to call gabbro, but I kind of like the name norite. It sounds more, I don't know, elegant in a way. The only way you can tell the difference between diorite and norite is if you take a thin section and you do a full elemental analysis. I'm not really worried about it. But you can say, oh, you know, I had this great, the Code of Hammurabi, but where do you find norite? You find norite here. Oh, look at this. Can you read that? Lunar sample. You find norite. Most of the samples brought back by the Apollo astronauts are norite. Ooh, moon rock. It's from the moon. No. The actual stone that was used, There's a particular mine in South Africa that's famous for all its platinum metals that it's located near there. That's where we believe it came from. So a little bit of language for you. Language of chemistry is kind of a funny thing. Here's some different representations, and just to point out that you might have an idea, oh, formaldehyde, using preserving cadavers or what have you. You might have an idea for a molecule and then you draw it up. There's a long process that went through, multiple bits of software, lots of people involved. Here's another example, styrofoam. The stuff you drink coffee cups out of, that's blown polystyrene. Styrofoam is this blue stuff used in buildings. The drinking cups, coffee cup, is not styrofoam technically. It's a trademark here. But chemically, this is how a chemist would draw it. But since this is a table and there's an artist involved, she wanted to have some long, skinny molecules. And so we might draw this molecule, oh, polystyrene, you might notate it this way. You might draw this molecule drawn out this way in the little squiggly lines at the end, meaning it goes on. So here's the way polystyrene actually looks on the table, because if you note the table, there's edges that are covered with it as well. There were a lot of people involved in this. Anybody from the class of 12 here? So when you get older, you say, don't you want to be 1, 2? Actually, I'm pretty happy being where I am. I hope you all are too. I'll mention one student in particular, Charles Zipe. Every molecule had to go through his computer, even though he was in Texas, because he had the software that we couldn't get everybody's software to talk. Just technical fun stuff. Charles was one of several students who'd taken glass blowing from me. He made a little caffeine molecule here. It's the molecule that's on my tie, in case anybody was wondering. Performance-enhancing drug, you can think of it as. So the quick question is, like, how you can't connect the chemistry and the art. How do you choose what goes on there? Who chose? Jenny Holzer made the choices. She was provided with a list of thousands of names. We drew up 1,500 names, molecules roughly. How many made it on the table? There's 715. Give the title is kind of a giveaway. What kind of molecules did you choose? You might choose a molecule that Hodge made or wrote about, like this one, azahelicine. You might use, ones in teaching. Students went through some of Hodge's teaching notes and basically drew up all the molecules, put a list out there. Molecules with interesting shapes like this one, housane, sometimes called pentaprismane, sometimes called the devil catcher. Molecules that had funny names. So Jenny Holzer developed this kind of affection for molecules. She found a website, Molecules, a silly and unusual name. So a bunch of goofy name molecules, some of them which I wouldn't say in public. You can argue that's not even a molecule. So the beauty of the thing is it's a teaching moment. It's like, is this a molecule really? Or is it just a transient species that I'm interested in? Molecules with social relevance, there are a lot of drugs on the table. Not nasty drugs. Drugs that might save your life, like this one, cisplatin, the most successful cancer drug out there. And molecules that fit in the space. I mentioned long, skinny molecules. So I went to the primary literature. And what do you find? There's a paper that was published about this particular molecule right here, and the name of it is blah, 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 blah. The title of the article is blah, 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 a long, skinny molecule. Okay, a little bit of fun. You'll find that when you draw molecules in 2 dimensions, it doesn't represent their 3-dimensionality. And one of the ways to do it is to put wedges on there, but even that doesn't always do the trick for you. So for example, this molecule over here with 5 atoms, there's a carbon atom in the middle. I got to get my pointer again. There's a carbon atom in the middle that's just assumed to be there, and then 4 different atoms are on there. There's 2 different ways of drawing it. And I'll show you how to do that in 3 dimensions. So if the stage lights are just right, and if you're sitting in the right place, you can say, oh look, there's the molecule and its mirror image. Can you see the mirror image in there? Everybody can see that. Where's that mirror image? If you take a look at this molecule and you say, oh, let's pull out its mirror image. Sorry, I got to pull out its mirror image. I have it back here. Yeah. We don't actually use purple very often. It represents iodine, but for today, I had to use, and yellow really represents sulfur and not chlorine, one of the halogens, but it's purple and gold. You got to do that. All right, here we go. So if you look in the mirror, you can see another see that molecule? Ooh. That was one of my favorite Hodge Markgraf demos, is to do this stereochemistry thing. So you've got 2 molecules right here. They both have the same molecular formula, the same boiling point, the same melting point, the same physical properties, with one exception. That is, when you take polarized light and you shine it on these molecules, that with one molecule, the light will start to turn in the right direction, with the other molecule it'll start to turn in the left direction. And the way you can tell that is you can say it has a non-superimposable mirror image. So you took the mirror image, so I got this molecule and I've got its mirror image, and then I try and put them together. Let's put purple together, let's put gold together, black, oh, white and green don't work. Two different orientations. You say, like, let's put the white and the green together. Oh, the purple and gold don't work. Let's put purple and white together. It doesn't work. And you can say this is kind of a novelty one, but if you take a look at real molecules like spearmint or caraway, nice big molecules. We could do a demo. I know, just broke a bond. These big molecules, how can you tell the difference between them? I could look at them with plain polarized light, or I could look at them with my nose. So here's a little chemistry demo here. We've got two molecules that are the same. They're mirror images of each other. Spearmint, negative. Caraway, positive carbones. So how do you smell these guys? Don't take them and go snort them, because you'll be smelling the same thing all day. You just waft a little bit, maybe give it a little squeeze. But, ooh, spearmint, delicious. And this one, caraway, it's like rye bread. Oh, class of '82, thank you very much. Help me out. Oh, we've got more. Ready? Who's Stephanie, you can help me out. Oh, right on your head. Ooh. No, we got some on the other side too. We can go this way. Little bottles, and you gotta be careful with these ones. If you look on the table, there are a lot of molecules, and it's not always clear which of these you're making. You might say, what difference does it make? Function follows form in chemistry. In art, it might be the other way around, but function follows form. And so the way the molecules behave depend very much on the shape. And these ones are nice, easy ones that you could eat or smell without harm. But many drugs exist in this kind of right-handed form and left-handed form. And one of them might be beneficial, and the other one might be harmful. I'll just mention thalidomide is one that kind of is familiar to the general public, kind of a problem drug name that way. Okay, a little bit more about molecules. Just for your amusement value, some molecules that weren't chosen. Molecules with funny names that aren't real molecules, like armpitin, are not on the table. Familiar things like crystal structures or DNA helices or large proteins, just too big. Ferrocene, the iron sandwich there in the middle, doesn't work when you try and sandblast that. Sorry. So a lot of them aren't on there. Also, transient species not on there. Atoms not on there. Some were just a little too cute. The nano ballet dancer, that's actually a real molecule. Somebody synthesized that. Een, ein, own. No, it doesn't exist. There's the table. Holy smokes. This is where you step back from chemistry a bit and you say, what's happening here? Sea of molecules, universe of molecules. This is where you know that there was an artist involved. There's a seam right in the middle, because you can't make a piece of stone quite that large. There's a seam right in the middle. Graphic design, you don't see the seam when you're out at the table. It's beautiful. Here's the key. Everybody asks, is there a list of molecules? There they are. We've got to thank a few people. Oh, class of '97, I got 97 in here. A lot of students involved over there. So this is part of the Williams story. Interaction, students doing research. We got over 200 students doing research this summer in the sciences, including the summer science program for pre-Frosh. I'll tip of the hat to Scott Snyder here, just received tenure at Columbia. Dave Vosberg, soon to be tenured at Harvey Mudd, in a molecule that they worked on, made it on the table. Really important to proofread, because here's an example of where there was a problem. If you look right in the middle there, you can say, ooh, there seems to be a line missing. This is the sort of thing, you can imagine 715 molecules, some of them are huge. Oops, better fix that. So how do you make this? Well, very interesting. Take a rubber mat, computer program, you cut a rubber mat like this, You stick the rubber mat on top of a piece of stone, and then you sandblast it. You sandblast it, and the beauty is this isn't the ultimate stone that was used, but it's pretty close to it. You get this nice black, and then you get a high contrast with the proprietary sandblasting process. Don't tell Rock of Ages. Here's how you do it. You take alumina, you blast it once, and then you come back with little iron beads, and then you get this beautiful white. You get the black and white contrast. Here's another little trick. If you look at the back side of this, this isn't quite the right stuff, but the pavers that surround the table are made of the same material as the table, just a different surface treatment to it. So it looks like a really strong contrast of gray, black, and white. Oh, here they are. Rock of Ages, little hand detailing. Sandblaster with the map, but you got to go in and look at it. Just that you can get a sense of here, if you look up at the upper right, this is one of the largest facilities I've ever seen. It was really fun to be in there. Wash it off. When it's wet, you can't see any of the molecules. When it's dry, beautiful contrast. Where is it sitting? You might recognize Jessup Hall and Morgan Hall there. There's a big hole in the ground a year and a half ago. 47 yards of concrete. That's 80 tons of concrete down below. Buried it, then installed it. Mark Cronus, amazing guy. He's got a piece of granite like swinging around over his head on little pieces of cloth. Good story about Mark here. He is the most impressive installer, but he's also not a chemist, and he was asking questions like, where's water? And one of my classmates, George All, chair of the visiting committee for WICMA, asked, he said, Jay, are there any dirty molecules on the table? If you look over here, there's a dirty molecule on the table. See this molecule here? It goes below the surface. Everybody says, oh, no, there's an error, you blew it. And it's like, no, actually, that was intentional. You can see the design here. There's a little wiggly line. That molecule is dirt. It's a humic acid for the chemists in the audience. Mark Cronus also said, where's water on the table? Well, there it is, H2O. And there's Hodge pointing at water, H2O, another represented. The simplest molecule on the table, water. Some would argue the simplest, the most popular molecule on there. But there's some other reasons on there. Mark Cronus installing, he said, why all the ho-ho-hos? Ho-ho-ho is an alcohol group, an OH group, but it's also Ohio. And you may know that Hodge is from Cincinnati, my father's from Cincinnati, and Jenny's a Buckeye as well. So there was accused of the connection there. A lot of molecules. I'll tip of the hat of Resorcinol, one of Hodge's best buddies working on it. Another story, which I'll just dispel right now, is I heard somebody, you walk around, people say all these things like, they even put a bow tie on it for Hodge. Actually, bow tie diene is a real molecule. Spiropentadiene, there's the reference for you. Journal of the American Chemical Society, like the most important journal in chemistry. There it is. There's the molecule right there. A lot of fun molecules. The table lives on, and I will just make a little note here that the subject, one of the first kind of studies of this is the thesis of Will Su, who, in addition to writing about Jenny Holzer's art, is one of the first recipients of the Fulkerson Leadership Fellowship. So he will be honored in that way. Oh, there's Jenny herself. Just taking a quote out of context, I encourage you all to touch the table. It's designed for that. She said, Jenny said something like, if nothing else, people will have a nice place to sit. At graduation, it was a very popular place to sit. And if you notice these people in the hats, some people are doing more than just like having lunch or listening to 500 names be read. But some of these people are actually, like tracing out what molecules are there. All fun. Thanks to all these people. But I could tell you one more story. It's a Hodge story, and I hope that some of you have heard this before, but I'll repeat it. This molecule right here, a prominent edge of the table, it's actually one that I asked Jenny if she could put it and make it a prominent one, is Disparler, the gypsy moth pheromone. It's one of the famous Hodge stories about, he developed a synthesis for this that's used to this day in teaching a 300-level chemistry course. And it's a fun synthesis. It's a multi-week synthesis. It's a complex synthesis. It's a chiral molecule, meaning it rotates polarized light like we did the demos here. Like maybe you're smelling in the audience now. Keep those passing around. I'm not smelling the spearmint up here. But if you succeed in this synthesis, it is a pheromone. It attracts. There are no human pheromones, but there are gypsy moth pheromones. If you succeed in this synthesis, then gypsy moths will come haunt you. So Hodge brought some of this home at one time and left it in his garage. And to Nancy's absolute, the late Nancy Markgraf, Nancy's absolute horror, the garage was just filled with gypsy moths. And he had to go out there with a vacuum cleaner to get them out. So, all right, so a little story. So I told Jenny this story, and I said, you think it would be okay if we painted a little disparler on the representation of disparler? Okay, you can talk about the art. And she said, can we get butterfly pheromone? Can we cover the table with butterfly pheromone? Maybe next time. So thank you all for coming on this beautiful afternoon. And I'll leave you with a Jenny quote. And of course, I'll be happy to answer any questions.